So Ziyad, accept all the people that we have in the lobby, and then we will wait a few minutes, and after that we will start the webinar. It's okay for you?
Yeah,
right.
That's okay.
Hi, Ziyad. Thank you.
Hi, Antonio.
We managed to get all right to Barcelona. The queue in the airport.
It was quite big. It was quite big. Yeah, that's true.
Yeah.
So we'll admit all the, yeah. So we'll start our next webinar in just a few minutes. We'll just wait 5 minutes and then we start it.
So, good afternoon, everyone. I'll be your moderator for today. My name is Claudia Brito, and I'd like to welcome everyone to today's Epicure webinar and how to profile your Python code. And basically, today we'll be joined by Ziyad AlBanoby, who studied at Alexandria University in Alexandria, Egypt, earning his degree in computer communications engineering. He specialized in CUDA software optimization and porting, focusing on algorithms on the GPU. He worked for 2 years at Bright Skies company, and in 2024 joined the high-level support team at the Barcelona Supercomputing Center. So I'd like to inform all of you that you can use the chat to ask all of your questions, and in the end we'll just do a Q&A and we'll discuss all of your questions. You can add these questions during the meeting, and then we'll just answer in the end. I'll be monitoring the chat activity regularly and ensure that all the questions will be dealt with in the end. And so basically we can now move to our webinar, and please keep your microphone muted. As soon as we add you, sometimes the microphone will be unmuted, so we are so sorry for that, but that's the team's problem. Unfortunately, we'll still have to solve that issue. So thank you all, and Ziyad, now it's your time. Thank you.
So hello everyone. Welcome to today's webinar. So today we'll be talking about how to profile your Python code. So as we all know, Python has been seeing a large increase in terms of code that is being written and deployed. And over the years, sort of performant codes have been sort of in decline. And so what's kind of perplexing is how come a language that is sort of slow is seeing such an increase in adoption as compared to performant languages, in particular in areas such as machine learning and image processing and things that you would consider would require a lot of performance. And the thing about that is that the Python ecosystem is very nice in that you can very simply just do a pip install and you would have your library up and running, and you'll be able to do whatever work or sites that you're doing. And the thing about the way that Python sort of gets around this is that despite Python being an interpreted language and C being a compiled language, what you're actually doing when you're calling these libraries in your Python code is that Python internally, what it does is that it calls into the shared library through the Python interface that is sort of provided by the library developers themselves. And what it does is that it dispatches through the CPython interpreter to your shared library through things that you link against the Python library, the C++ library, which is why when you're running whatever machine learning or whatever sort of program that you're doing that requires high performance, it's actually running sort of a compiled library already, and it doesn't actually sort of execute on the Python interpreter. Now, when you're running your code, you run it basically on a machine, and you buy a CPU, you spend enough money on that CPU, and you want to get every ounce of performance out of that CPU. And if you're Barcelona Supercomputing Center, you have a bunch of GPUs, a bunch of CPUs that you want to maximize the usage and get your money's worth for these clusters. And so you better be able to execute as many different kinds of programs as possible. And the thing is, with current modern day general purpose CPUs is they basically treat a program and data the very same thing. At the end, you have some data, you have some instructions on how to perform your whatever computation that you want to do in the data, and you delegate sort of the task of running these program instructions on the CPU. And due to the fact that you want to run as many programs as possible, you want to be able to just simply write the program to memory and then run it immediately. And that shouldn't require a lot of overhead in doing so. Now, memory, as we know, is much slower as compared to computation. And this is due to the way it's primarily due to cost management, because when you buy a CPU, at the end you want to sell it. Or when you sell a CPU, if you're Intel or Nvidia or ARM or whatever company, you want to make money off of it, but you also want people to buy it as well. So the problem that comes with treating sort of your program and data as memory is that you have this bottleneck that memory is much slower. And this is where you spend most of your R&D effort, because you really want to perform computations or whatever science you're doing. You want to run it as fast as possible and sort of increase the time to solution and productivity. And so you end up with memory being sort of the one that's pulling CPU down. And so it could be the case. It could be the case if you're running a very inefficient program that you are not maximizing sort of your memory, and in that case you would be compute bound. But this is very less. This case is very much less seen in real world as compared to the case where you have memory and data that you're trying to read off of disk. And you're trying to, previously as well, with all the computers, it used to be the program size that mattered, but nowadays it doesn't quite matter, just due to the fact that CPU development has gone quite well. And what this is quite known in the literature is that it's the von Neumann bottleneck. And people try and get around the von Neumann bottleneck by trying to introduce caches and putting things in the CPU, sort of branch prediction and all of these things. And what they're trying to do is they're trying to reduce the latency of a particular memory access. And what you want to do is you want to execute your program as much as possible. So when you run a Python program, at the end of the day, it's going to run on a CPU and it's going to call into some data. And if you're in an HPC environment, the data can be coming sort of from disk or from your DRAM or from your network. If you're running sort of a distributed MPI or a distributed Spark or Hadoop or whatever, and that could be coming from a network file system, or you're doing sort of collective communication. And this is where you would have issues when you're running a program on the CPU, primarily if you're fetching data from a very far off place, because you actually have to get the data to the CPU to perform the computation on them. And so when the goal is when you have a program, you run into this sort of particular cycle where you first try to measure the program. And what you're interested in measuring your program is just you want to get an overview of the performance sort of characteristics of your program when you execute it on this particular sort of CPU network or disk architecture that you kind of have. And depending on where you run it, these things might be different. And you want to use the appropriate profiler to help you identify sort of the bottleneck that you should be able to, that you would like to later optimize. And using the appropriate profiler is really crucial because it would allow you to get the appropriate sort of insights into what you would need to change in the code such that you would be able to better utilize your program. And so for this particular sort of presentation, we're mostly going to be invested in measuring our program, because identifying the bottlenecks and optimizing your program are very much sort of specific to your case or specific to the program that you're running. And every program has sort of a particular performance characteristic depending on the nature of the algorithms that it uses, or the way that it is written in terms of how it makes use of the existing sort of software infrastructure that's provided for it. And so when you try to profile a program, there are multiple sort of levels that you can try to profile your program. And the idea is to pick the appropriate level such that you can quickly find your bottleneck. So basically, profiling is kind of a search problem where you try to search through the code, try to find, or through the execution of the code as well, where is the bottleneck. And there are different layers that you can try to profile an application on. So you can profile it to the machine level. And this is where you look into the performance counters of your CPU. And then you try to figure out what part of what functional unit of the CPU is my application not making good use of, or if you're running it on a GPU, for example, you would be interested in identifying sort of how much utilization that kernel is making. If you're using tensor cores, maybe how much of the code is using tensor cores, how much of the DRAM are you saturating, or how much of the cache hits you have. So you would first, so instead of trying to figure out from looking at the code, what you decide to say, you decide to look at the program from a basic, so that from the lens of the machine, and you're trying to figure out what is my final code doing on that particular machine. Or you can decide to look at the execution level of your program and try to figure out where in the particular program's flow of execution is the bottleneck. And what you can, because so you cannot really entirely reason through, not all metrics are the same. So you cannot entirely reason through summary statistics about the characteristics, or about the performance characteristics of your program. So it could be that you have sort of a binding issue due to your execution level, where your program really has a bad sort of binding, and your threads are competing for particular cores, and you wouldn't be able to sort of see that directly if you look at the machine level. So you'd be interested in how your sort of program interacts with the operating system, interacts with sort of the resources that it runs on. And your goal here is to identify sort of where in the source code does this particular activity exhibit itself? Where does this manifest in the execute as a performance problem through the source in the source code? And well, you can also profile at the source code level, and this is much expensive, where you try to look at every sort of line of code, and you instrument it, or the profiler sort of instruments it and tries to derive metrics from that. At the end of the day, you want to find a performance problem as possible, move on to continue your work, and get your results. And that entails using the right sort of tool for your profiling task. Different profilers have different overheads, different profilers have different sort of metrics that they show you. And so the idea is to get comfortable with a few of these in this particular talk, though there are many others that you should actually explore and take the opportunity to try out, because maybe my workflow works for me, but at the end of the day, something else could work out for you. And in particular, sort of Python provides you this tracer. Insight Systems is an NVIDIA profiler, and you also have C profile, and that is also native to Python. And you have Line Profiler that is also native to Python. You have Intel vTune if you're running an x86, and you have also Intel Advisor, also x86, and other ones as well. And so Linux Perf sort of gives you. It comes up with whatever operating system that you have installed. And you have TorchProf if you're also running sort of machine learning workloads. You can profile just about any type of application with whichever profiler. It just depends with how much ease you're able to extract the information that you're looking for to quickly sort of optimize your particular application. And the overheads, of course, that each of these profilers sort of exhibits. One thing that you want to ensure when you profile your program is that you want to ensure that you're measuring your actual kernel time. Much of the overhead about program execution may not necessarily be in your particular kernel or your particular sort of code. It could be the overhead that is associated with using the profile, or the overhead that is associated with running your sort of particular kernel. Or maybe it could be that you might have perhaps had a bad run and you had your timing sort of off, you do whatever outliers. So the idea is to run your simulation, run your program for an adequate time, take a look at the outliers, remove the outliers, average things out. You want to also be running exclusively. You don't want other programs to sort of interfere with you, so you can allocate that through Slurm using the exclusive flag. And you want to ensure sort of a repeatability such that you do not have to manually execute your profiling every time. It's much better if you use something like Huga or Reframe to be able to have a workflow that runs the profiling and or benchmarking task and be able to deliver the results for you. And much better if you're able to integrate that into your CI/CD to be able to detect sort of performance regressions or things of that sort. And this is an example of a profiler where you have a particular sort of a very large sort of increase with regards to sort of the overheads associated with it. So the idea is to be aware of the overheads of the tools you're using, know the limitations, know which tool to use. And today we're going to be exploring a few, but I encourage you to go out and check out other tools as well. So the first one we'll be exploring is cProfile. And cProfile is a Python native sort of, it comes with Python packaged and you can use it directly. It works basically on profiling Python level, CPU time. It does work with GPUs, it doesn't work with TPUs, so if you're trying to profile those. It might profile the CPU overhead associated with executing these, but it's not profiling sort of the kernel time or the metrics that you'd be interested in. And usually the way these profilers come in is that you have the profiler that collects sort of the traces on the metrics, and you have the visualizer that sort of tries to visualize these metrics for you and presents it to you. So cProfile works sort of programmatically. You can put it inside your code. You can try to profile your sort of complete program using just cProfile as such. And one thing to be aware of is that you only profile single-threaded applications on, you're only able to profile single-threaded applications using cProfile. So if you have a multi-threaded application, maybe then cProfile is not very well suited for you. You might check other profilers such as Scalene. And so here's just me expanding on how you would profile your sort of cProfile program. Here's how you would do it. You're going to profile your complete program. This is your output file. This is your particular script. If you want to profile only a particular region of your program, then maybe something programmatically might be of that sort might be interesting. You can also sort of pass in a string to a particular function that that cProfile will be able to execute, for instance, and have it output the profiler into this particular extension, which would be loaded by the visualizer. And another one is that, for example, let's say you have a sort of a function you want to execute and you want to provide the global context and the local context, because this function can be executed by another function. So you might be interested in providing it the locals for this particular scope and the globals as well for this particular program. And you'll be able to sort of profile for this sort of particular string of Python, the particular runtime overhead associated with it. And so we start off with a very simple example where we are trying to compute this sort of this 2D FFT. We're trying to compute for every point here. We're trying to compute sort of this particular function. And this is the internal function that is sort of called by this slow sort of annotated slow function. And what we see here is that this particular function takes 46.2 seconds, which is, we don't know, we just know that this function sort of takes a long time. And then what we do is that we profile it. You can, if you're running in a Jupyter notebook, you can sort of profile it using %prun. And what you're able to see here is from the output of prun, where you cumulatively accumulate for execution, is that here we see that DFT slow is our function. It's called once, and it calls the function that we just saw above. It calls it about 4,096 times. And we see that the per call time is 0.12 seconds. And we see that it accounts for 47.6% of the total time or execution time of our program. So we try to look further we visualize our program using SnakeViz, and that we visualize it as such. What you see here is sort of a flame graph, and in a flame graph you have the total execution on top, and you have the breakdown for this particular sort of stack, or for this for the time. So each rectangle sort of corresponds to the proportion of the total time or execution time of the program that it takes. So for example, you can see here that for this main.py, you see only 36.5 is sort of spent in DFT slow, and for DFT slow, most of the time is actually spent by our DFT function. Here we can filter our stack depth, so we can limit sort of the functions that we can have for this particular sort of stack trace. And we can also sort of cut off, so we can say functions that take less than 0.01 seconds, we don't need to show those. We're interested in functions that take more, because we expect perhaps the performance of our program takes more. You're also able to see sort of the functions sort of listed out, and you're able to see the same total time and the number of times that it gets particularly called for, and what is the time sort of per call for this particular function. And you're able to sort of search through particular functions that you might be sort of interested in. So if we remember from our previous talk, someone introduced sort of Numba, and what we can try to do is that we can try to JIT our particular function. And while we're not interested in this particular sort of talk with regards to optimization of Python, what JIT does is that it takes whatever sort of code right here and just transforms it into CPU sort of native code that it would be able to sort of execute. It would make much more better use of SIMD and things of that particular sort. And we're able to see here that for the same sort of function that we had before, we're able to see that it no longer takes time, and we're able to sort of see that our program now takes 886 milliseconds instead of before. Now, before we move on to sort of our next sort of profiler, one thing that you ought to think about when you are optimizing or profiling your application is that at the end of the day, your program is executing a set of functions, and these functions depend on particular inputs. And these functions and the thing that is sort of limiting your program execution are your true dependencies. Those are things that you cannot compute, that you cannot compute without having had their inputs sort of computed. So on a sequential processor, you would try to find a schedule that would sort of particularly deal with these sort of dependencies, and you would sort of linearize your particular DAG and execute that. The way you go about optimizing your program is trying to identify sort of the critical path of your application and trying to either reduce the critical path, and that could be perhaps by so for example here, if you're able to provide as many resources for this particular input right here, so if you're able to sort of provide more resources right here, you're able to sort of reduce the critical path length, at least with regards to this particular section of your program. Now, the world is not perfect. There's no free lunch. You have a CPU, you have a limited number of cores. And so at the end of the day, the goal is to try to identify sort of which tasks would benefit more from better sort of scheduling. And this would be sort of due by exposing more parallelism, making better use of your hardware, making better use of the things that sort of come for free that you're not really making use of in your program. You can also try rewriting your algorithm to expose more parallelism, so you can reduce sort of the sequential path that a particular sort of function takes and make it as much as parallel, and like rewriting the algorithm as parallel. Of course, that is a lot more effort. You can also try to extract sort of common blocks between functions and have those make better reuse of the data, so you compute the data once and reuse them. And an example of this, just right quickly, is that, for example, if you have a machine learning model, here it's a convolutional neural network, and you see sort of these sort of particular sort of computation blocks where it's computing a one-by-one convolution, a bias and a ruler. You see this sort of happening over here and here and here. What you could do, or what actually TensorRT does for you, is that it combines it for you as one sort of particular kernel, and it further even sort of combines these two together to make better use through use of the data locality. And that way you're able to sort of reduce the critical path length of your program. Now, once you have sort of your C profile, what you can do is sort of you can take this particular sort of view of your program, and you're able to sort of identify sort of the paths in your program that sort of consume the most amount of time. And really the goal here is just to hint at you where are the things that are taking the most time. And here is the command for how to generate this sort of particular trace for your particular profile, and it outputs it as an image that you can sort of have a look at. So if we take a closer look at our graph, what we see here is that we see that for each of these nodes, so basically all the nodes that are highlighted in red are ones that are on the critical path of our program execution. We have the percentage time that is that this sort of particular time percentage of our total execution time that this sort of particular link sort of takes, and how many times that function calls into this sort of particular function. And what you're able to see here is, here would be the total time spent on this sort of particular spent in this sort of particular function, including time spent in other functions that this function calls. And here is just self time, and self time of the function, which just means sort of the time that really sort of direct instructions or direct statements sort of execute on. So just timing sort of the inner body of the function without timing the other function calls that come with it. And below that, you have the number of times that this particular sort of function got called for. And for our particular sort of DFT example, what we have here is that our function got called for 1496 times, and we see that the self time and the total time of our program execution is quite the same. So what you're looking for is something similar. Now, another thing about another sort of shortcoming of this view is that you can have different paths of your program execution sort of go into the same sort of common block or common function, and you wouldn't, there may not necessarily be related to one another. So, for example, if for example you have these programs, even though these programs sort of have different sort of Python sort of programs, you have very much similar graphs, and even then similar sort of critical paths in the program, and except only for a few things, such as the number of times that it gets called for, you see that the same critical path is there, and this is really quite a nice thing. But this is also another very much similar sort of graph with a very much similar sort of share of the program execution, but they might have different sort of execution characteristics on the CPU. They sure do have the same timings, but the way they interact with the CPU, the way they interact with the input is very much different. And so, for example, let's say you're running sort of this very simple indirect indexing, and where you have, once you've sort of provided a particular sort of input that is sorted, so you take very less time, and then on the second time you take even more time, because the index, you're incrementing at random indices, and that takes more time because you are doing more cache misses of things of that sort. And the problem with graph is that they would show up as just one complete sort of node with the summary statistics. You wouldn't be able to discern whether it was your input that was an issue or not, and for that case, you would use a timeline-based sort of visualizer to do that, to view that. And this is where sort of this profiler sort of lags short, but it allows you to see which parts of your program or which sort of critical paths of the program that you should be looking to optimize for. Once you've identified your function, then you can sort of try to look at the function and profile for that particular function and look sort of which instructions are the ones that are causing that particular issue. And for that, we move into our next profiler, which is line profiler. And line profiler is now natively a part of Python as well. And so line profiler also comes with a lot of overhead because it measures sort of every particular sort of line, and that may not be sort of ideal if you try to profile your complete program by exporting this environment variable. So ideally, you want to use something where you just sort of place this decorator over your function and just print your statistics at the end of the file, at the end of your program execution. And so, for example, of a particular sort of case where line profiler might help you identify something like that is if you're, for example, using NumPy, and due to the way Python is very much flexible in its syntax and due to the richness that the libraries sort of give you, you might be doing something very much innocent where you are doing sort of this particular axis and well, selecting the rows, then you're selecting sort of particular columns from these rows. And internally, what NumPy would be doing for you is that it would be sort of copying, creating sort of copies, and it would lead to sort of inefficient sort of accesses. Whereas if you did it sort of this way, you would be much more efficient by simply just giving everything to NumPy and letting it know. And this sort of particular example is, say, if you have machine learning sort of a pipeline where you randomly sort of mask out certain areas or perturb certain areas. This might sort of be one of your bottlenecks on pre-processing. And in fact, we actually had a particular sort of use case in one of our sort of projects where we had a weather forecasting model, and a particular weather forecasting model was using a sort of NumPy, or well, it was using ZAR, and ZAR is kind of an abstraction of a NumPy, and with index into sort of these chunked data sets. And we'd have this particular indexing, which really, as you can see here, was the one that was consuming the most amount of time, and it executed just about every line over here, but it was the one that was consuming sort of the most amount of time, and you can see the time per line execution for that particular, and percentage of time for this sort of particular function. You can see also the decorator here. And what you see here is that what we did is we decided, okay, we can really sort of do it much better. And this is my colleague over here, Saxena. He's the one who introduced this. Basically, what he did is that he used Dask, and what Dask does is allows you to parallelize over the indexing, and that sort of kind of gave us a much faster sort of speed up, at least for this particular execution. And now that we were able to identify sort of what particular things are wrong with our Python code, in particular with regards to the lines, what function bodies are there, we might be also interested in the behavior of our program as it executes on our CPU or GPU, or, for example, as we later see, we are also TPUs, but not with Insight Systems though. And so Insight Systems works with Python code. You can do it using the GUI, or you can do it through programmatic inserting annotations, or you can just do it through the CLI by Insight Profile. There's another one that's called Insight Compute, and this allows you to profile into your particular kernels. So you can think of this as the equivalent of line profiler for your kernels, but we will not be going through this one over here. And so if you want to profile your Python application or whatever sort of application that you're interested in profiling with Insight Compute, Insight Systems, what you would do is you would do -t, and -t is your target, sort of the things that you want to profile for. And we're interested in CUDA. OSRT is the OS runtime. NVDX is if you have annotations in the code, and if you're using sort of the CU libraries, you would use that. And if your program is sort of doing communication, such as MPI or Indical, you would be able to sort of also see these, and you can also look at the behavior of the global interpreter lock if you are using an older version of Python that is older than Python 3.13. And if you look at Insight Systems, what we see here is first you gotta allocate a node, because you don't want to run this on the login node, and you don't want to certainly not disturb anyone trying to log in and do the work. So here you place your program, your working directory, and similar to the CLI, you would choose what sort of particular things you would like to sort of trace, and you would start to trace, and then later you would be able to stop the trace. Now we quickly gloss over sort of the things that Insight Systems gives you. You're able to see the SM occupancy or your GPU sort of utilization kind of in real time with regards to kernels that are executing a particular program. Here you see this sort of very small summary view where low CPU utilization. Here you see the NVDX sort of markers where you try to annotate the logical execution of your program such that it becomes more discernible for you to identify sort of what parts of your program are responsible for this particular behavior. You're able then to look even further into the program's execution and see sort of what percentage of time on a particular stream on the GPU are you spending on kernels or compute, and what percent of time are you spending on memory? And then you're able to sort of even look even further deeper and see sort of what percentage is spent per kernel for the whole execution of the particular program. And you're able also to see if you're doing more copies to the GPU or more copies out of the GPU, so you're able to sort of more sort of know where to focus your optimization efforts. It also gives you sort of a summary statistics for your kernels. The nice thing is that it gives you the average, the median runtime, the minimum, maximum, and the standard deviation, and the percentage of total time execution of your program. You're also able to do the same thing for memory transfer times, where you're able to see sort of how much memory did you transfer in total, how many times did you do that on an average, what is the size of the data that you're transferring. You're also able to see what percentage of the total time are you spending on each sort of direction of the copy or memory operations, and you're able also to see a combined one where you see sort of as compared to your whole program execution, are you doing more copies as compared to compute, or are you doing more compute? Which kernels are, which sort of memory operations are the one that's taking a long time? And you're able to sort of filter through sort of certain parts of your program, because many parts of your program, for example, if you're running sort of a solver here in this particular case, what you're able to see is that you are really sort of looking at a per time step, because your trace sort of execution sort of is periodic and it repeats. If you're able to see, for example, the GIL behavior. So GIL is the global interpreter lock, and if you're running sort of multi-threaded code, what would happen is that you would have a thread that would hold onto the GIL, and then it would execute, and then they would give away the GIL after some time, and then the other sort of thread will take the global interpreter lock and do its execution. And you're able to see this sort of behavior very much in the code. And we see here we're doing a very sort of simple kernel where we're just multiplying two numbers and just passing in the memory. And what we see here is that we see this particular thread holds the GIL, and this one is waiting for it, this one is computing, and this one holding for it. And you see this sort of takes 15 seconds. But it's not really parallel. And here you see sort of the threads, then which sort of particular core they're running on at a particular time, at this sort of particular time. And now here's a sort of a truly no GIL behavior, where you see here all of the threads are sort of concurrently running, and this is what you're trying to sort of achieve in your sort of Python program. Another nice thing is that nowadays you're able to sort of run GPU kernels on Python. You're also able to sort of use NSYS to see that, and you can, here we annotate portions of our program to see, to sort of mark them logically. And here we're doing a sort of a hosted device and a kernel execution, and excuse me, and then do a device host over here, and you're able to sort of visualize sort of that these sort of parts are responsible for this host that occur during this sort of logical part of your program here. And then you're able also to see your sort of kernel execution time and things of that sort. And if you're running sort of a machine learning workload and you're interested in running sort of compute and communication at the same time to make better use of your resources, you would be able to sort of see that where you have sort of Nico sort of running or executing on a separate stream, as well as you have also your PyTorch sort of computation for this sort of backward pass executing. And here you're able to see with regards to your Python sort of execution, where in your Python program is it doing, and here it's sort of evaluating the backward for an embedding layer. And here you see it's calling, so you can see PyTorch sort of calling into NVIDIA's CUP library. And so you're able to sort of see internally into your program. And you can also take these NSYS traces. So let's say you're doing a global change that would affect your complete program, or you're running sort of things across different runs and you want to compare them. The nice thing about NSYS is that it gives you the ability to export your metrics into SQLite, and you can sort of directly query them. And so they also, NVIDIA also gives you sort of a set of reports, a sort of recipes, so to speak, existing, but you can also do just about your own. If you just go ahead over to this link, and you will see that the SQLite schema just about gives you the ability to query for about any metric that you're interested in. Here we did a global change, and we're interested in how much percent of that affect the runtime of the particular function. And so you can see this sort of summary statistics simply by querying an SQLite file, and that's a nice thing about ANSYS. The last sort of profiler that we'll be going over is XProf. And XProf is a very nice profiler that sort of comes in with JAX, and it allows you to sort of profile PyTorch, TensorFlow, and if you're using JAX as well for your ML workloads, you're able to run it on TPUs because JAX as well as HLA sort of allow you to run on TPUs as well as sort of GPUs as well. The quite unfortunate thing is that you cannot sort of interactively run it as much as you would do with ANSYS. But keep in mind that ANSYS doesn't work for TPUs, and it only works for GPUs, and that too NVIDIA GPUs. And so programmatically, you would have to insert sort of statements in your program. And the way you would go about that is that you would place this at the area you want to trace. You would put in the output directory that you want to output the trace to, and then when you stop the trace, you want to put stop trace, and then you can put a trace annotation, which is very much similar to your NVTX, where you want to logically label a particular part of your program. And the way you would do is just you would, like we saw before, start trace and stop trace. And once you're done with your computation, what you can do is that you can launch sort of XProf, you can pass it to the log directory that you had passed it earlier to see that particular trace. Now, if you're running on an HPC environment, you very much auto-allocate a node to view even the trace, because if you're profiling a long run, the processing for the trace might be expensive. And so you can either allocate a node and do SSH forwarding, as we see here, or you can copy things directly onto your computer and view them. So here we just simply sort of put in the host name for the compute node as part of our SSH config, and we put in sort of the port that we want to sort of forward and expose the XProf server to our sort of local login node, so that we're able to sort of run this and see it. Of course, if your compute nodes have internet, which I don't think most other systems might have it, but on Mare Nostrum we do not have compute nodes that have access to the internet, so you ought to sort of do the SSH forwarding. And the nice thing is that you can see basically a very sort of summary statistics about sort of your program execution and profiling, and you can see sort of the breakdown in terms of so if you're running a machine learning training, and you can see the per step time in milliseconds, or however, at least here it's milliseconds. I suppose you can change it as well. You're able also to have the same view that ANSYS sort of provides you. So this is very much nice. So if you're used to profiling things on the GPU and you want the same view on your TPUs, you're very much able to do so. For this particular trace we're running on GPUs, however, you're able to see your memory operations running on the different streams. You're able to see which parts of your source code sort of are responsible for the XLA ops that are executed, and our framework ops as well. You're able to see with regards to the CPU code, sort of the things or that execute or by the threads of your program that maybe PyTorch or the underlying framework is launching for you. You're also able to see the flame graph that we are very much familiar with SnakeViz, and we're able to sort of see, you're able to sort of click on this, and then you would be able to sort of see where in the timeline does it correspond to. And yeah, so this was basically a quick sort of overview of our of the set of profilers that you can sort of use with Python. And the most important thing is to sort of use the profiler that works out for you. Use the profiler that gives you the right amount of information to allow you to optimize your program. At the end of the day, you want to optimize your program as quickly as possible and move on to the next important milestone or the next important feature that you're doing. Yeah, so experiment around, choose whichever you like, get familiar with the profiler, run simple examples. The important thing is to understand the limitations of your profiler in terms of overhead or memory consumption. And yeah, that's about it for this sort of presentation. And thank you very much. Thank you. Any questions are very much welcome.
Thank you so much, Ziyad. I think we just have one question here,
Yeah,
but
okay.
I think it's relating to the traces and what you actually mean by a trace.
Okay. Oh, okay. Well, okay. So a trace basically, well, okay, so this is what you would call sort of a trace. A trace is basically sort of the events that you're trying to measure over the execution of your program, and they're recorded in that sort of particular file. And so when I say trace, it could be whatever, at least maybe I'm using it very much leniently over here. Again, a trace would be, in the strict sense of the definition, would be sort of things that you record over the execution of the program, and you're able to sort of see them step by step. But in some of these profilers, you're mostly able to see sort of the summary statistics. But for example, in ANSYS, an ANSYS output file is what you would call a trace, for example, but you may not necessarily call the other ones trace as well.
Hopefully that answers the question from Gabriel. Actually, I have quite a few questions. I've been
Perfect.
working with PyTorch and several other Python solutions and frameworks.
Mhm.
The thing is, profiling things actually adds overhead, right?
Mhm.
We cannot escape from that.
Mhm.
But after you've studied so much of these tools, which is the most the less intrusive approach, and actually the solution that has less overhead?
So I would go with NVIDIA's tools. I'm a big fan of them. Of course, you should again. So the nice thing about this, at least with regards to NVIDIA tools, is that the amount of metrics that you collect, sort of per trace, is very much important, because if you collect all the metrics, that is by all means going to be a huge overhead. It just depends on what the amount of information that you are comfortable discarding, and the amount of information that you just want to have a look at in order to understand the performance profile of your application. So at least for NVIDIA, at least for PyTorch, if I'm trying to profile with ANSYS, what I would try to do is that I'm interested in the MVTX markers and the kernels executed on the GPU and in the nickel communications. If I wouldn't really be interested in profiling Python, I wouldn't really be interested in looking at the things that Python is doing, unless it's sort of data loading, then I would not use ANSYS for that, and I would use I would use sort of the other sort of Python profilers, where if my code of the pre-processing is native to Python, because again, you can insert MVTX markers in the code to know sort of what proportion of your program is spent. And of course, these are very less costly as compared to trying to sort of profile. So you might just mark a region where you think, or based on a preliminary measurement that takes the most amount of time, you mark it, you see it in the trace. Okay, I need to investigate this part more. And then you decide to extract only information for this particular part. And here, for example, you look at the profiler and you're able to sort of profile, you start profiling after sort of a particular set of seconds, and then you can sort of limit the profiling to 10 seconds, or you can limit by how many sort of outputs, how many sort of profiler sort of events that it collects. So you should limit the information if you think it's taking overhead. You shouldn't just profile every part of your application. You should kind of have a sense of where the overhead is, and then slowly use the profiler to dig into that particular part. And if you're doing sort of a multi-GPU, you would take the ANSYS profile traces, and then you can sort of export them to SQLite and be able to see, to pre-process them to see, for example, what ratio, perform summary statistics on them to determine maybe if there is a load imbalance where a particular node is doing more computation than other nodes, or if another node is sort of being the one that drags other node in a particular sort of collective. So you're able to even extend sort of the profile of the power of the profiler by just simply querying the database and trying to determine your own metrics. I hope that answered the question.
Yeah,
maybe
actually, yes. And I think we have two more questions here, and then I'll go back to mine. And I think is Sharon U that says, when writing C, C++, used to profile also the cache mismatch and branch prediction. Yes. Until now, is using Python programmatically as a glue code and never thought to tune the performance. Is branch prediction, for instance, using it to check shape of array in every FFI calls inside a loop also matters in Python bytecode?
So if you're running things through the Python bytecode, you would be able to see where in your particular Python interpreter that is, if it is a particular hotspot. And branch prediction, until now I'm using Python programmatic as a glue code, never thought to tune the performance. Is branch prediction. You have to first make sure that branch prediction is actually the issue. Because branch prediction is a hardware thing. It's not really a software thing. So you'll be interested in the performance counters of your program. And the performance counters come from the Python interpreter. And so when you run perf, what you're going to be seeing is you're going to be seeing the performance of the Python interpreter for your particular application. So if there is a branch misprediction, it would not be much your fault. It would be much fault of your interpreter. And at the end of the day, the interpreter is a generic executor of any particular Python program. So if you can avoid calling into things in Python that would cause it to do branching, of course, that would be much good. That'd be better. But if you cannot, then it is what it is. And you first have to make sure that branch prediction is indeed the issue. And you can look into sort of you can look into perf, or you can look into sort of tools that are built on top of perf. So Intel provides a tool for top-down analysis, CPU top-down analysis. Basically, it's a Python script basically that hooks onto perf and collects the metrics and groups them for you, so you know if your front-end bound and front-end bound is being associated with sort of the instructions that you're fetching and the branch prediction logic, or your back-end bound where you are bound on the functional units of the GPU, so seeing the integer units. Maybe you're executing more floating point operations than you should, or things of that sort. So yeah, hopefully that answered your question.
Hopefully it does. Actually, Emilio Villa, I think, said something that it was my following question, which is, which of the presented tools is best suited for a Python program running on CPU only, on multiple cores and so on, but actually focusing on CPU, not only GPU. And I think NVIDIA tools actually work really well to GPU environments. But when you are looking at only CPU, CPU frameworks that have been running there, Python frameworks, which is the best tool to use there?
So if again, this is sort of my bias over here, but again, it depends on the code that you're running. So if I want to get summary statistics, I would just put NVTX markers over the code and try to see where and when sort of these different parts of the code execute, and you're able to sort of see the Python global interpreter log. If you're using an older version of Python, you're able to see the behavior of the global interpreter log. So you're able to sort of discern if how much share of the total execution time of the program is each thread able to get from the global interpreter log. And so if you doing multi-threaded core, assuming the threading is on the Python level, then I would just put mbtx markers or just simply run nsys and see sort of the threading behavior. Now, if the threading is in an underlying layer, for example, let's say you're calling into a C++ library that uses sort of threads, then what you can do is that you can sort of use Intel vTune, and that would allow you to see, you would just profile it as any sort of C++ program, but the problem is that you would see a lot of other sort of stack traces that you may not necessarily be interested in. So it could be just a bit of too much information trying to find your way through the part that is responsible for the threading overhead in the underlying library. If the threading again is on a Python level, then I would just try to profile it. If you can profile it as a single thread, which is a very simple solution, just turn off the thread, profile the program, see what it's doing. Reduce if you're providing it a large input size, reduce the input size so that you're able to profile in a reasonable amount of time. And yeah, these are the things. I mean, I would look into it if it's once I turn it into a serial program, I can just use line profiler or to look into a particular line once I've identified the function using cprofile. And yeah.
Okay, and just to follow on these questions, actually, does these frameworks actually, and it may be a bit far-fetched, but for instance, profiling code in a broad way can actually be used to be using tools for like going to the kernel, seeing the system calls and so on.
Yes.
How would that actually be able to go into these frameworks and have that feature? For instance, using eBPFs and so on. I'm not an expert on that, but I've actually worked with people that have been using eBPFs, not on this setting probably on HPC, because there are several limitations of going to kernel and see what has been done. But how could actually using that be helpful for these tools?
No, I don't think these particular tools are meant for this particular use case. I think if you're doing more sort of into kernel level profiling, then you would use a different set of tools. At least if I understand correctly, by kernel level, you mean the Linux kernel and the way your program sort of interacts with the operating system and the way the operating system forwards these to the kernel and then how it forwards it to the drivers. So in that case, this particular set of maybe Intel Advisor may be useful, but because Intel Advisor sort of gives you the best of both worlds, where you're able to look into the function calls that it's doing, and you're even able to look at the assembly, and then you're able to look at the microarchitectural profile. But I don't think other tools would be best fit for this particular use case. The other tools, at least in this particular presentation.
Yeah, it makes sense. And just to close, and it's just for my curiosity, when doing workload characterization, are these tools helpful, or will just add overhead that actually the workload characterization is not actually suitable?
Can you provide me maybe an example to be more precise?
For instance, I'm trying to run a PyTorch workload, a training workload of AI, and I want to understand the patterns and what is being done by the Python processes that are being launched, and using that traces for actually doing workload prediction or workload characterization for following jobs. Would like these tools help me understand which job is actually been running? Will these tools actually add overhead that we don't really understand what is the job that has been running? It's like I'm just trying to understand at which degree and the granularity to which these tools can actually help us.
So when you're doing workload characterization, while this is an area that I'm not familiar with, so I would confess that I'm not familiar with workload characterization in terms of predicting how well a job is going to be, but you can use the traces from NVIDIA Insight and pre-process them, and you can use also the traces from the TorchProf to pre-process them. I would err on the fact that on using NSYS, since it's more of a runtime thing, it doesn't quite really add a lot of overhead as compared to profiling with perhaps the Torch profiler or other things of that sort. It also depends on the metrics that you want to collect for performing your performance characterization. So when you're doing something at a runtime level that NSYS is doing, it's not as harmful or is not as intrusive as would be other methods that would try to instrument the code. So for example, if you're doing Insight compute, or if you're trying to get sort of the line runtimes to be, and you want to use that to characterize the workload, the overhead would be much more just due to the fact that you're collecting more information per measurement. So ideally, you just want to collect as little information with as little interruptions to the straight line or code path execution of your program. And so for that, I would be using sort of in NVIDIA Insight or things that hook into the loader and just sort of dynamically link in place of the actual libraries, and then actually then call this particular function that is trying to look into. But yeah.
Yeah, it makes sense. Yeah. Okay. I'm not sure if anyone has any more questions. If so, please do so. I want to thank you, Ziyad, once again.
Thank you.
Ziyad,
Thanks so much.
once again. It was really interesting.
Thank you very much. Thank you.
And actually, there were a lot of tools that I was not aware of. So it will be interesting to actually test them out. So thank you so much for this thorough introduction to several of these tools. And hopefully, we'll see you again.
Thank you. Thank you so much.
Time.
Thank you.
I will just
try
to, okay, probably is this one. I will share my screen once again. Thank you all for being here as well. Actually, we have a hackathon that will be done in a hybrid manner. So you can go to Stockholm, visit Stockholm, or go do it online. And basically, it Python meets HPC. So if you have any problems with your Python code, you can actually go to this hackathon and try to use the mentors to solve them. So I think you all should attend and see if you can actually improve your code and try some of these profiling tools. Try even Numba that was talked about in the last webinar. And thank you so much once again. Hopefully I see you all on the hackathon, and thank you, Ziyad, once again.
Thank you
as well.
Thank you very much. Thank you.
So thank you all. Stay tuned.
Thank you.
Bye everyone. Thank you.